At all relevant times, you must wear safety glasses, safety boots or steel cap shoes, overalls, and heavy-duty insulating gloves. The working area must be clean, clear of all obstructions at all times, and recognized safe working practices must be observed strictly at all times. There are a very large number of high-performance camshafts available on the aftermarket today for both the shovel head and Evolution Big Twin engines. On the surface, all of these cams may appear to be the same. In fact, however, they are very different, and the differences have a big impact on engine performance. The selection of our camshaft becomes much easier once we understand some basic camshaft terminology: duration, lift, overlap, lobe center line, lobe separation angle, and profile. We must learn to appreciate how each of these factors impacts the performance of our engine. Here we have a diagram that outlines the basic physical elements of our camshaft: the base circle, the ramps, and the lobe. The term duration refers to the amount of time it takes the lifter to travel up and over the cam lobe, to once again rest on the camshaft's base circle. Duration is illustrated by the yellow area in this diagram. This time or duration is always measured in crankshaft degrees. As the lifter is raised by the cam lobe, its motion is linked by the push rod to the rocker arm, which in turn applies direct pressure to the valve stem to open our valve. The amount of time our lifter spends off the camshaft's base circle directly controls how long our valve is kept open. Therefore, duration directly affects where in our RPM range our engine will produce its maximum horsepower and torque. For example, the longer the duration, the higher will be the RPM needed to produce maximum horsepower. At the same time, our power in the lower RPM range will be reduced. The longer the valves remain open at low RPMs, the harder it is for our piston to compress the fuel-air mixture effectively. Lack of piston speed and excessive duration result in poor volumetric efficiency, thus reducing the compression or cylinder pressure. The longer the valves remain open at high RPMs, the more fuel-air mixture our piston is able to suck in. With higher piston speeds, the volumetric efficiency is greatly increased on the intake stroke. On the compression stroke, the fuel-air mixture is quickly and effectively compressed, giving us more horsepower and torque. As we can see from this diagram, the standard intake duration for a stock 80 cubic inch Evolution motor is between 208 and 222 degrees, and the stock exhaust duration is between 202 and 236 degrees. Now, if we have a stock California 80 cubic inch Evolution motor, both the intake and exhaust durations would be approximately 178 degrees. In contrast, a high-performance camshaft would have durations between 240 and 265 degrees. Any duration above 265 degrees we would associate with a racing or ultra-high performance camshaft. As shown in this diagram, the optimum cam durations for each performance level will be higher for shovel head motors than for Evolution motors, due to design differences between them. We note that general performance rules differ appreciably in the case of 4-valve heads. 2 intake valves allow a much greater flow and fill the cylinder more quickly than the single intake valve of a stock head. This is due to the fact that the combined circumference of 2 smaller valves is greater than that of 1 large valve, and it is the circumference of the valves that controls the flow of the fuel-air mixture into and out of our heads. To calculate duration, we need to find 2 constant points on the cam lobe ramp between which the lifter is above the camshaft's base circle by a fixed distance. There are 2 industry standards for this distance: 20 thousandths and 53 thousandths of an inch. In this demonstration, we will use the more popular industry standard of 53 thousandths to find our duration constant points. First, we must find and set a zero or top dead center point for the front cylinder on the degree wheel mounted on our crankshaft. Please refer to the stroker number 1, the bottom end video for the full procedure. We temporarily assemble the front tappet block, complete with hydraulic lifters, the front piston without rings, the wrist pin without keepers, and the front cylinder. Next, we mount a dial indicator to the top of our front cylinder so that we can accurately gauge when the piston is at top dead center. Then a dial indicator is mounted on the top of our front exhaust lifter. It is very important that the stem of this dial indicator is seated at 90 degrees as well as being in the center of the lifter. To confirm that we are indeed on the compression stroke and approaching top dead center, the front intake lifter must be just beginning to fall, as shown here on this shovel head tappet block. Now we take our lifter over the cam lobe to the heel or base circle of our cam. It is here that we must zero the dial indicator on our lifter. Once zeroed, we continue to slowly rotate the crankshaft until we find exactly where the cam lobe ramp begins, as shown on this diagram. The cam lobe ramp begins and the base circle ends when the dial indicator starts to move off zero. We keep rotating the crankshaft until our lifter has traveled far enough up the opening ramp to be 53 thousandths of an inch off the base circle of our camshaft. Holding the crankshaft in this position, we record the reading on our degree wheel, which is 68 degrees before bottom dead center, or 248 degrees before top dead center. To avoid any errors due to backlash in the gear train, we make sure that we rotate the crankshaft in one direction only. Please note that we have removed the cam drive gear solely for demonstration purposes. Continuing to slowly rotate our crankshaft, we force the hydraulic lifter to ride up and over the cam lobe until we are again at 53 thousandths from the base circle on the other side. Once again, we hold this position and record our degree wheel reading. This time, we are at 28 degrees after top dead center. Now, by adding both of our measurements together, we find the duration of our front exhaust cam lobe to be 276 degrees. We repeat the above procedure exactly to find the duration for the front intake cam lobe, which in our case is 266 degrees. Remember, to accurately compare the durations of different cams, the durations must be measured using the same constant points on the cam lobe ramp, either 20 or 53 thousandths of an inch off the base circle. Increasing the cam lobe and valve lift will generate more horsepower and torque by simply allowing more fuel-air mixture into the cylinder without compromising our power at low RPMs. Ideally, to take full advantage of our valve lift, the valve would have to open almost instantaneously. Unfortunately, this is not possible due to a couple of factors, one being valve spring failure. Secondly, the design of the head also strongly controls the flow of the fuel-air mixture into the cylinders. Therefore, it is absolutely essential that the flow capabilities of our heads match the physical requirements of our motor. Both the valve-to-valve clearance and the valve-to-piston clearance specified by the manufacturer must be strictly observed, so that valves and pistons do not collide and destroy one another during motor operation. As a general rule of thumb, the maximum intake valve lift in a stock Evolution motor is approximately 25% of its valve diameter. In contrast, the intake valve lift in a stock shovel head motor is approximately 20% of its valve diameter. Racing motors will have intake valve lifts that are 30 to 35% of their intake valve diameters. The stock Evolution motor from 1984 to 1987 has a valve lift of 0.472 inches. The stock Evolution motor with L cams from 1988 to 1991 has a valve lift of 0.495 inches. The stock shovel head motor has a valve lift of 0.390 inches. And the stock pan head motor has a valve lift of 0.412 inches. Just looking at the duration of different cams does not tell us everything we need to know. We must also look at the maximum or net lift of each individual camshaft. There are two types of lift: cam lobe lift and valve lift. Net cam lobe lift refers to how high the lobe of our cam will push the lifter off the heel or base circle at its maximum point. To measure the net cam lift, we place our camshaft firmly between the centers in our lathe. This time, we place the dial indicator directly onto our camshaft. Once again, we zero our dial indicator to the base circle diameter, as we did previously. Then, we slowly rotate our camshaft until the needle starts to move off zero, where the ramp of our camshaft begins. We mark this point. We continue to rotate the camshaft until the dial gauge registers the highest point of our cam lobe. This point is 344 thousandths of an inch off the base circle, and this measurement of 344 thousandths is in fact the net lift of this cam lobe. There is an alternative method that we are able to use only if the cam lobe for which we are trying to find the lift has a base circle that occupies more than 180 degrees of camshaft rotation. That is, if the angle between the start of the opening ramp and the end of the closing ramp, including the lobe maximum, is less than 180 degrees. For this type of cam, we can use a 1 to 2 inch outside micrometer to accurately measure the base circle diameter, which is 1.075 inches. We must ensure that the anvils of our mic are not on either of the cam lobe ramps, so that our measurement is accurate. Next, we mic the cam lobe itself by placing one anvil on the highest point of the cam lobe and the other anvil on the base circle. If we were to draw a straight line from anvil to anvil, it would pass through the center of the base circle. Once in position, we take the reading from our mic for the cam lobe height, which is 1.419 inches. Now, we subtract the base circle diameter of 1.075 inches from the cam lobe height of 1.419 inches, leaving us with 344 thousandths for the net cam lobe lift. Most high-performance camshafts have specialized cam lobe ramps that are designed to lift for more than 180 degrees of cam rotation. In this case, we cannot use an outside micrometer to measure the base circle diameter. In this instance, we will need the following specialized measuring equipment: a height gauge, a dial indicator, a V-block, and a granite surface plate. This plate must provide us with a surface that is absolutely flat to within 2 ten-thousandths of an inch over its entire face. The needle of the test indicator is designed to be placed in various positions. In our case, we prefer the needle to be at 45 degrees to our test indicator. The dial indicator is mounted on the foot of the height gauge. We clamp our camshaft firmly in the V-block and place both the height gauge and the V-block on our surface plate. For cam shapes where the lobe ramps cover more than 180 degrees of cam rotation, the only diameter that can be measured directly is that of the camshaft bearing surface, which is on the crankcase end of our camshaft. This is measured with a micrometer to be 812 thousandths of an inch. We will use this bearing surface as the reference for deriving the base circle diameter. We position the needle of our test indicator on the highest point of the bearing surface and zero our dial indicator to this point. From the vernier scale of our height gauge, we find that the top of the bearing surface is 2.990 inches off our surface plate. Using the fine adjustment on our height indicator, we slowly raise the foot of the height gauge, being extremely careful not to bump the needle of the dial gauge. This needle must remain in exactly the same position for the entire measurement. Next, we move the height gauge over so that the needle of our dial gauge is positioned above the base circle in question. Using only the fine adjustment of the height gauge, we lower the needle until it just touches the high point of our base circle. We must be sure that this measurement is made on the base circle itself and not on the start of one of the lobe ramps. With the needle of our dial indicator resting on the diameter or high point of the base circle, we continue to use the fine adjustment to slowly lower the foot of the height gauge until the dial gauge is again zeroed. Then we read the vernier scale again. The surface of the base circle is measured to be 3.120 inches off our surface plate. Note that if the needle has been bumped, or if it has changed position accidentally for any reason, we would have to start the whole procedure over again. We now calculate the height differential between our base circle and the bearing surface. We subtract the height of our bearing surface above the surface plate, which is 2.990 inches, from the height of our base circle above the plate, which is 3.120 inches. This gives us a height differential of 130 thousandths of an inch. The base circle diameter is derived by adding twice this height differential, or 260 thousandths, to the bearing surface diameter, which is 812 thousandths. This gives us a base circle diameter of 1.072 inches. This procedure must be repeated for each of the base circles, since all of the cam lobes are ground individually and therefore their base circles may vary. Valve lift is the maximum distance the valve is raised up from the valve seat. We use the following formula to calculate our valve lift. We multiply our cam lobe lift, 344 thousandths, by the evolution motor rocker arm ratio, 1.6, to give us a valve lift of 550 thousandths of an inch. Note that if we were using solid lifters, we would have to account for the effect of backlash clearance. The accepted value of 1,000th of an inch would be deducted from the cam lobe lift value before we multiply it by the rocker arm ratio. Now, if we are building any other style of motor, the rocker arm ratio would be as shown. Evolution motors, 1.6 to 1. Shovelhead motors, 1.43 to 1. Panhead motors, 1.5 to 1. Knucklehead motors, 1 to 1. Side valve motors, there are no rocker arms. The term overlap refers to the situation where both lifters are off their respective base circles together and both valves are open at the same time in one cylinder. That is, the inlet valve is beginning to open and the exhaust valve is almost closed. Cam manufacturers control the amount of overlap in a cam by varying the position of the exhaust cam lobe and the intake cam lobe relative to one another for the same cylinder. For example, the farther apart the exhaust and inlet lobes are angled, the shorter the overlap. The closer they are, the longer the overlap. Here we are using a crane cam, part number 1-1003. The manufacturer's specifications for this crane cam state that the intake valve starts to open at 23 degrees before top dead center, and the exhaust valve is closed at 28 degrees after top dead center. To calculate the overlap of this cam, we add together the intake valve opening at 23 degrees before top dead center and the exhaust valve closing at 28 degrees after top dead center, giving us an overlap of 51 degrees. Here is the procedure we use when we are unable to obtain the valve timing specifications from the manufacturer. We set up our degree wheel and dial indicator as we did previously for measuring the duration. This time, however, we mount our dial indicator on the front exhaust lifter and zero the indicator to this particular base circle. Next, we slowly rotate the engine until the front exhaust lifter is traveling down the return ramp of the cam lobe toward the base circle. We stop rotating when the dial indicator shows that we are 53 thousandths of an inch off the base circle. At this point, our lifter is about to roll off the return ramp onto the base circle, and the front exhaust valve is within the standard lift tolerance of being fully closed. Our degree wheel indicates that this event occurs at 28 degrees after top dead center. Moving our dial indicator over to the front intake valve lifter, we find where the front intake cam lobe begins to open the inlet valve. We take our degree wheel reading from the point where the front intake lifter leaves the base circle by 53 thousandths of an inch and starts to lift the front intake valve off of its seat. Our degree wheel indicates that this event occurs at 23 degrees before top dead center. In most cases, when we increase the duration of a cam, the overlap will also increase. However, some manufacturers are able to vary the amount of overlap without increasing the duration of the cam. With a little planning, we can make this overlap work for us. For example, at higher RPMs and with a tuned exhaust system, a strong vacuum is set up by the exhaust gases as they escape through the slightly open exhaust valve. This vacuum helps to suck in fresh fuel-air mixture, just as the inlet valve starts to open. Quickly filling the cylinder with new fuel-air mixture dramatically improves the volumetric efficiency and the flow through our heads, giving us more power and performance. At low RPMs, however, the slightly open exhaust valve works against us, because the inertia of the expended gases is too low to create the vacuum we had at high RPMs. Here the opposite effect sets in. An exhaust reversion is created, where the exhaust gases are able to flow back into the cylinder and contaminate the fuel-air mixture. This greatly reduces volumetric efficiency and results in dramatic torque and power losses. With a longer or extended overlap, exhaust reversion can be so severe that the pulses of exhaust gas can force themselves back through the inlet valve and into the carburetor, creating major problems at low speeds. One simple way to stop exhaust reversion and compensate for the loss of power and compression at low RPMs is to mechanically increase the compression ratio of our engine. The cam lobe center line is a fictitious line that runs through both the highest point of our cam lobe and the center of the cam base circle. We use crankshaft degrees of rotation with respect to top dead center to locate the center lines of both our intake and exhaust lobes. The intake lobe center line is the most important of the two, since the opening of the intake valve directly controls the time allotted for compression to take place. The exact position of our intake lobe center line with respect to top dead center indicates how advanced or retarded the timing of our cam is. The following calculation is valid for symmetrical cam profiles. For asymmetrical profiles, the cam lobe center line can only be located experimentally, using the same setup we use to measure cam lobe duration. Taking the intake lobe duration of 266 degrees, we divide it by 2, giving us 133 degrees. This is the crankshaft rotation between the intake valve's defined opening point at 53 thousandths and its point of maximum lift. The standard opening point was located at 23 degrees before top dead center during the procedure to measure overlap. Therefore, we now subtract 23 degrees from 133 degrees to locate the intake lobe center line at 110 degrees after top dead center. We do a similar calculation to find the exhaust lobe center line, except that the exhaust valve's closing point is subtracted in the calculation, and the center line is located on the other side of top dead center. Half of the exhaust lobe's duration is 138 degrees, from which we subtract the closing point, 28 degrees after top dead center. This puts the center line of our exhaust valve lobe at 110 degrees before top dead center. In our particular case, the intake and exhaust lobe center lines are symmetrically placed about top dead center. This will not always be the case, due to the many different cam designs and grinds. When we talk about advancing or retarding a camshaft, both the intake and exhaust center lines are changed. For example, we can retard our camshaft by 3 degrees, bringing our intake lobe center line position to 113 degrees after top dead center. We can do this by removing and slightly rotating the camshaft drive gear. Now, all cam events will happen later in our engine cycle, since all the cam lobes are ground into the camshaft itself and cannot be moved separately. By retarding the cam in this manner, we will increase cylinder pressure at high RPMs and improve our top-end torque and performance. The trade-off for increasing our top-end performance is that the cylinder pressure and the torque will be reduced at low RPMs. Now, the opposite change would result if we were to advance our camshaft by 3 degrees, bringing our intake lobe center line position to 107 degrees after top dead center. The result would be an increase in cylinder pressure and torque of our engine at low RPMs, and at the same time, a decrease in cylinder pressure and torque at high RPMs. If we advance our cam, we must recheck the intake piston to valve clearance. The camshaft will have moved the maximum valve lift point closer to top dead center, bringing the piston and the intake valve closer together. Similarly, if we retard our cam, we must recheck the exhaust piston to valve clearance. If we advance our cam by 4 degrees, we will lower our engine's power band by 200 to 300 RPM. Conversely, if we retard our cam by 4 degrees, we will raise the power band by 200 to 300 RPM. If we have to advance or retard our cam by more than 4 degrees to get desired performance from our engine, then we have selected the wrong cam for this engine. Our only recourse is to select another camshaft that is better suited to our requirements. Under no circumstance should a rough trial and error method be used to find the correct cam timing. Rotating the cam by just 1 tooth in either direction translates into an adjustment of approximately 18 degrees, which is far too great a change and may cause major problems. We refer to the angular separation between our intake lobe and exhaust lobe center lines for the same cylinder as the lobe separation angle, or LSA. This angle, also known as the lobe displacement angle, is measured in camshaft degrees only. We cannot adjust or change the LSA as it is ground into the cam by its manufacturer and can only be changed by regrinding the cam. Two camshafts may appear to be identical by having the same duration and lift. However, different lobe separation angles will result in different performance, even for identical values of duration. It is the LSA that cam manufacturers use to control the valve overlap and duration, and thereby the power band of their respective camshafts. Making the lobe separation angle smaller without altering our duration will cause the intake valve to open sooner and the exhaust valve to close later, thus increasing valve overlap. Also, a smaller lobe separation angle will extend the time that both intake and exhaust valves will be closed at the same time, which will greatly increase cylinder pressure. This benefits us by increasing our horsepower and torque in the low to mid RPM range, at the cost of reducing our top-end performance. A good example of an effective low to mid cam would be the Andrews EV46 cam, which has a smaller lobe separation angle of 102 degrees, an overlap of 42 degrees, a lift of 495 thousandths, and a duration of 246 degrees. On the downside, if the lobe separation angle is too small, for example, under 95 degrees, the cylinder pressure will dramatically increase to the point where the fuel-air mixture will prematurely detonate. This will cause our motor to ping at low RPMs, as well as greatly decreasing the performance of our engine at high RPMs. Consider now the effects of a larger lobe separation angle. Our intake valve will open later, and our exhaust valve will close sooner. This reduced overlap will result in a drop in the intake manifold vacuum and a loss of cylinder pressure. Larger lobe separation angles will generally move our engine's power band up into the top end, giving us a flatter torque curve and better idling. In general, larger lobe separation angles, such as 112 degrees, tend to be more forgiving when the duration, overlap, and lift are not properly matched to our engine. Many cam manufacturers, in an effort to use a longer duration more effectively, will use a slightly wider lobe separation angle to stop the valve overlap from becoming too excessive. In our high-performance engines, we prefer to use cams with lobe separation angles between 100 and 108 degrees, allowing our engines to breathe better and produce maximum torque and horsepower. This compares with stock big twin cams that have a lobe separation angle of about 112 degrees for better idling and emissions control. For this particular 104-inch engine, we have selected an indexable crane cam, part number 1-1003, which has a lobe separation angle of 110 degrees. To calculate the lobe separation angle of our cam, we find the crankshaft degrees between its intake lobe center line, 110 degrees after top dead center, and its exhaust lobe center line, 110 degrees before top dead center. The total angle between the two center lines is therefore 220 crankshaft degrees. Now, we must convert these crankshaft degrees to camshaft degrees by dividing by 2, since 1 camshaft degree is equal to 2 crankshaft degrees. We divide 220 crankshaft degrees by 2 to give us 110 camshaft degrees, the value of our lobe separation angle for this particular cam. There are 2 types of cam profiles. The first profile type is called symmetrical, where the shape of the closing ramp of the cam lobe is the mirror image of the opening ramp shape. In this case, the cam lobe raises and lowers the valve lifter at exactly the same speed. The second type of profile is called asymmetrical, where the shapes of the opening and closing ramps are very different. In most cases, the design of the opening ramp forces the valve to open very quickly, reaching maximum lift rapidly, and keeps the valve near maximum lift for a much longer time. This dramatically improves the flow through our heads. The shape of the closing ramp lowers our valve slowly, which greatly reduces the stress on our valve train. Most high-performance Evolution and shovelhead engines use asymmetrical cams. We always refer to the cam manufacturer's specifications for correct spring pressures and tolerances. The faster a high-performance asymmetrical cam opens or closes a valve, the stronger the spring pressure required to prevent the valve lifter from losing contact with the cam lobe surface at high RPMs. Insufficient spring pressure will allow the valves to float off their seats, thus changing our timing. We degree our camshaft to our engine to ensure that the valve timing matches the cam timing specified by the respective cam manufacturer. The closing of our front intake valve is especially critical. In the case of our crane cam example, our front intake valve will open at 23 degrees before top dead center, and then close at 63 degrees after bottom dead center, or 243 degrees after top dead center, for a duration of 266 degrees. Our front exhaust valve will open at 68 degrees before bottom dead center, or 248 degrees before top dead center, and then close at 28 degrees after top dead center, for a duration of 276 degrees. It should be remembered that all of these angles are measured at a distance off the respective base circle diameter of 53 thousandths of an inch. In high-performance engines, where that extra 1/100th of a second makes all the difference between winning and losing, the cam timing in our engine must match exactly the camshaft manufacturer's recommended cam timing. In milder street engines, we usually allow a tolerance of 2 to 3 degrees in meeting the timing specifications of either cam. That is, our front intake valve could close anywhere between 61 degrees and 65 degrees after bottom dead center, and we would consider this valve timing to be acceptable. Remember, if we have to adjust our camshaft by more than 4 degrees, we have the wrong cam and must select another one. The tolerances and clearances we used in assembling the crankshaft and the bottom end in general will vary enough to greatly impact our camshaft timing in relation to our engine. This is why we must degree our cam to our particular engine configuration. To degree our camshaft to our engine, we must use the degree wheel that we previously mounted and zeroed to top dead center when measuring the duration, the lift, and the other physical characteristics of our camshaft. We place our dial gauge in the center of the front intake lifter, using the same techniques we used earlier when setting up the gauge on the front exhaust lifter. With our dial gauge securely in position, we rotate the cam forward until the lifter is on the heel or base circle of our front intake cam lobe, and then zero our dial gauge. We start to rotate the camshaft until the intake lifter has traveled 53 thousandths of an inch up the opening ramp. At this point, we read our degree wheel. Our front intake valve starts to open at 23 degrees before top dead center. Continuing the rotation, we force the front intake lifter up and over the cam lobe onto the closing ramp. We stop rotating immediately when our dial gauge is again at 53 thousandths off the base circle. Our degree wheel now indicates that the closing point of our front intake valve is 63 degrees after bottom dead center. It is the separation between the closing of our front intake valve and top dead center that determines where our particular camshaft will develop power in the engine's RPM range. In our case, the closing of the intake valve is at 117 degrees before top dead center. To arrive at this value, we first shift the reference for the valve's closing point from bottom dead center to top dead center by adding 180 degrees. That is, 63 degrees after bottom dead center is the same as 243 degrees after top dead center. Then, using the 360 degrees symmetry of the circle, we subtract 243 degrees after top dead center from 360 degrees to give 117 degrees before top dead center for the intake valve's closing point. Cam timing adjustment. Looking at our gear case assembly, the front face of the camshaft rotates counterclockwise when in operation. To advance our cam timing, we must rotate the camshaft counterclockwise within the camshaft drive gear. Shifting the camshaft in the same direction as its normal rotation moves all valve events closer to top dead center. To retard our cam timing, we do the reverse. We rotate the camshaft clockwise within the camshaft drive gear, thus moving all valve events further away from top dead center. Just for the purposes of demonstration, let's assume that we found that our front intake valve closed at 65 degrees after bottom dead center, which is the same as 115 degrees before top dead center. In order to match the crane cam timing specification for the front intake valve, we must move the closing back to 63 degrees after bottom dead center. From our previous calculation, we know that this point is also 117 degrees before top dead center, which means that we must retard our cam's timing by 2 degrees. To avoid any confusion, we mark the front face of our cam drive gear with an A and an arrow in red marker to show the correct direction to advance our cam timing. Similarly, we mark an R and an arrow in black marker to show the correct direction to retard our cam timing. Since we are going to do all of our calculations on the rear face of our cam drive gear, we must also mark this face with the respective advance and retard directions, making sure that they appear reversed from the front face markings. We use a red marker to indicate the advance side and a black marker to indicate the retard side of our locating keyway and the corresponding positions of these marks on the cam drive gear. If we did not have a keyway in our shaft, We would just mark the drive gear and camshaft in the same manner. Next, we must find the equivalent linear distance that we must rotate our drive gear on the camshaft to achieve the correct valve timing. Using a 1 to 2 inch outside micrometer, we measure the diameter of the shoulder behind the drive gear to be 1.209 inches. Note that this diameter will vary from cam to cam. Multiplying the diameter by pi, 3.1416, gives us the circumference of this shoulder equal to 3.798 inches. Now we divide 3.798 inches by 360 degrees to arrive at a relationship between linear and angular measurements for our cam. In our case, we find that rotating the camshaft by 1 degree produces a linear movement of 106/10,000ths of an inch on the shoulder. To change our cam timing by 2 degrees, we must rotate the camshaft within our drive gear by approximately 20,000ths of an inch or a half millimeter. So to retard the closing of our front intake valve from 115 degrees to 117 degrees before top dead center, we rotate the camshaft counterclockwise in the rear face of the drive gear 20,000ths of an inch from its original position. Remember, the directions for advancing and retarding shown on the rear face of the cam drive gear are reversed from those we showed on the front face of the drive gear. Carefully, we mark the right hand or advance side of the locating keyway with a red marker and its corresponding position on the drive gear itself. We do the same thing for the left hand or retard side of the locating keyway, except that we use a black marker. Some cam manufacturers, such as Andrews, help us by permanently machining the matching lines on the drive gear for the locating keyway at their factory. Continuing with our example, we wish to retard our cam timing by 2 degrees. We will do this by rotating the camshaft so that the black or retard side of the locating keyway moves counterclockwise by about 21,000ths from its original position. This starting point is indicated by the black mark on the drive gear. Taking a set of dividers and an outside micrometer, we adjust the setting of the dividers to 21,000ths of an inch. Next, using our dividers as a guide, we clearly mark the new position for the black or retard side of the locating keyway on our drive gear. Going to our press, we rest the drive gear securely on a set of parallels and gently press the camshaft out of the drive gear. Next, we flip the drive gear over on the parallels so that the factory timing marks are facing downward and we can plainly see our marks. We lightly grease the camshaft to make reassembling easier. Then, using the black mark and the penciled line on the drive gear as our guides, we carefully insert and rotate the camshaft until the black side of the locating keyway lines up with the inside edge of our penciled line on the drive gear. With the camshaft straight and turned to its new position, we gently press the shaft back into the cam gear until the gear sits firmly against the shoulder of the camshaft. If by chance the camshaft twists and moves out of alignment with its new position in the drive gear, we must press the camshaft out again and repeat the connection procedure. Once we have the camshaft reassembled, we replace the cam in our engine. We then repeat the degreeing measurement to confirm our calculations and to prove that we have indeed retarded our valve timing by 2 degrees. We may have to repeat this entire procedure a few times until we provide the desired cam timing. With our camshaft properly positioned to meet the crane specifications, both the intake and exhaust cam lobes will provide 143,000ths of an inch of lift at top dead center. If we advance or retard our cam timing by any more than 4 degrees from the recommended point, we run the risk of increasing our valve lift at top dead center, which will reduce our piston-to-valve clearance and increase the possibility that pistons and valves will collide. Not all cams are designed to provide a continuous range of timing positions. For those who want an easily set but limited choice of timing changes, Crane Cams has developed the High Rollers series of camshafts. These camshafts, which have multi-index cam drive gears, are designed to quickly and accurately advance or retard our valve timing by just 4 degrees. Each cam drive gear has keyways marked R, O, and A that are spaced 120 degrees apart. There are also 3 corresponding R, O, and A timing marks on the circumference of the cam drive gear. The red dot shown on this gear tells us the class of fit for this particular cam. We have placed the key in the keyway marked O because this position will give us the widest power band. When we replace the camshaft back in our engine, the O on the circumference must line up with the pinion gear timing mark, and the slash mark must line up with the breather gear timing mark. If we had chosen the A, or advanced keyway, we would have to line up the corresponding A on the circumference of the drive gear with the timing mark on the pinion gear and the slash with the timing mark on the oil breather gear. In summary, the advancing or retarding of our cam timing will move the power band in our engine up or down by 200 to 300 RPM respectively. Changes from the cam manufacturer's specifications should not exceed 4 degrees of advance or retard. And finally, under no circumstances do we advance or retard the camshaft by just 1 tooth from the original timing marks in the cam drive, as this would drastically change our valve timing by 16 to 18 degrees. When we replace any stock camshaft with an aftermarket high-lift cam, we must make sure that our camshaft, in particular the rear intake cam lobe, is able to rotate freely past the housing for the pinion shaft bearing race in our crankcase. If the rear intake cam lobe is hitting this housing, we must take our crankcase to a machine shop and have them remove the top section of the bearing race housing. Be sure that this change, which is required to give necessary clearance for the cam lobe, stops before it cuts into and weakens the pinion race itself. The resulting clearance between the rear intake cam lobe and the pinion shaft bearing race housing should be at least 0.010 of an inch. As our lifters pass over their respective cam lobes' maximum lift points during rotation, the direction of force exerted by the valve springs via the lifters suddenly changes from the front side to the rear side of the cam lobe. This causes the cam drive gear to ever so slightly kick back during its rotation. As a result of this slight kickback, the cam drive gear teeth will rock back and forth against the pinion gear teeth. This movement is called backlash. If we have more than 0.002 of an inch of backlash in our gear train, the directional change of the cam drive gear will result in an audible click. This cam gear noise can easily be mistaken for a bad lifter roller or a collapsed lifter. However, no real damage will result, even where there is excessive noise. We have found 0.002 to be the minimum amount of backlash that will prevent individual gear tooth overloads. A tight-fitting pinion shaft gear and a cam drive gear will result in both gears trying to climb one another, thereby producing a very noticeable howling or whining noise. This condition of tight-fitting cam drive and pinion gears must be remedied immediately. Otherwise, the two gears will quickly destroy each other's teeth and bearings, if allowed to operate for any length of time. To solve this problem of zero backlash, we must choose either a smaller pinion gear or a smaller cam drive gear to give us our minimum backlash of 0.002. In our case, we prefer to select a smaller pinion gear because then we don't have to reset our camshaft timing. Both the cam drive gears and the pinion gears are available in approximately 0.001 of an inch increments on their respective pitch diameters. This permits custom fitting of a drive gear with a pinion gear to give us the correct backlash of 0.002, allowing our camshaft to operate efficiently and quietly. First, we measure the pitch diameters of both our camshaft drive gear and pinion gear. For this, we must use a set of dowel pins that are 105,000ths of an inch in diameter, which are for camshafts 1990 and earlier, and this designated by a single groove or no groove around the front face of the cam drive gear. For camshafts 1990 and later, which are designated by 2 grooves on our cam drive gear, we would use dowel pins that are 108 thousandths of an inch in diameter. To select the matching pinion gear for our crane cam's camshaft, we must use 2 dowel pins that are 105 thousandths in diameter and mic the pitch diameter of our camshaft drive gear. We place 1 dowel pin firmly between the teeth on one side of the cam's drive gear diameter, and the other dowel pin is placed firmly between the teeth on the opposite side of the drive gear diameter. Holding both dowel pins firmly in place with a rubber band, we use a 2 to 3 inch outside micrometer to measure the pitch diameter of our drive gear, which in our case is 2.7473 inches. Referring to our cam gear and pinion gear chart, we find that our cam drive pitch diameter of 2.7473 inches falls between 2.7472 and 2.7476 inches. This drive gear, therefore, has a designation of orange, and its corresponding pinion gear is also orange. It is not possible to place both of our dowel pins on the diameter of our pinion gear due to the odd number of gear teeth, so we place only 1 pin on the diameter. Now, the corresponding pin has to be placed on the opposite side of the diameter, but this point passes through a gear tooth, so we have to offset our second pin against this tooth, as shown in this diagram. To quickly correct an already existing problem of excessive gear whining, we remove and mic the pitch diameter of our existing pinion gear and select a pinion gear that has a 2/1000th smaller pitch diameter. Now we do the reverse to correct the problem of the excessive clicking sounds by selecting a pinion gear that has a pitch diameter that is 1 to 2/1000ths larger. When using aftermarket camshafts, we first replace the stock cam bearing in the cone with a high-performance cam bearing. Now, we must determine exactly how much end play we have in our camshaft. To do this, we must temporarily install our crane camshaft, complete with thrust plate, into the gear case. This procedure will also require us to install a cone cover gasket and to correctly torque the cone into position. With that done, we mount a dial gauge so that it is seated squarely on the end of our camshaft. Using the lifter block holes for access, we press the cam hard up against the crankcase and zero our dial gauge. Once the gauge is zeroed, we push and hold the camshaft hard up against the cam bearing, again using the lifter block holes. Our dial gauge indicates that existing camshaft end play is 80 thousandths of an inch. A camshaft must have some end play, and the minimum end play we have found to work is 5 thousandths of an inch. The factory allows up to 50 thousandths maximum end play for stock Evolution engines. For more detailed information, please refer to the camshaft installation sections in the Evolution motor and shovelhead motor video manuals. We prefer the end play in our camshafts to be about 10 thousandths of an inch, or 1/4 millimeter. To correct the end play value of 80 thousandths that we just measured, we must find a hardened thrust washer that is approximately 70 thousandths thick, using a set of dial verniers. The hardened thrust washer that we've selected for installation is 72 thousandths thick, which will leave us with 8 thousandths of camshaft end play. We remove the cone and camshaft and place our hardened thrust washer between the end of our camshaft and the thrust plate. We coat all mating and bearing surfaces with assembly lube. We also coat our oil breather gear with assembly lube before installation and align its timing mark with the corresponding mark on the camshaft drive gear. Using a new cone cover gasket, we torque the cone into position. Then we must physically check the camshaft end play with a set of feeler gauges to confirm that our procedure has provided us with 8 thousandths of an inch of end play. If for some reason camshaft end play has changed and falls outside our limits, we must repeat the whole procedure until the results are satisfactory. Valve lifters, which are also referred to as tappets, come in 2 varieties, hydraulic and solid. Cams are ground specifically to use with either hydraulic or solid lifters. It is the cam profile which determines which type of lifter we must use. Cams ground with very sharp ramps and smaller durations, such as those found in evolution motors, typically use hydraulic lifters. Hydraulic lifters have a needle bearing roller which enables them to maintain contact with cam lobes that have extremely aggressive ramps. Hydraulic lifters rely solely on oil pressure to maintain a zero valve backlash clearance, even when the cylinders expand with heat. Use of these lifters produces a relatively noise-free operation. The downside feature of hydraulic lifters is the very fact that they rely on oil pressure for proper operation. This means that they are also very susceptible to any fluctuations in oil pressure in our engine. For example, when we first start our engine, the oil is cold and thick, making our oil pressure slightly higher. This in turn overpressurizes our hydraulic lifters, forces the lifter's hydraulic pistons up past their normal operating positions, and alters our valve timing. The altered valve timing will cause our cold engine to idle roughly until it reaches its normal operating temperature, at which point our oil pressure will be at its design value. The hydraulic pistons will return to their normal operating positions, and the original valve timing will be restored. The oil pressure is also dramatically increased when we run our engine at high RPMs, creating the same problem of overpressurized lifters. This is often referred to as the shock absorber effect. Once again, changed valve timing causes the valves to float, and our engine loses power and runs rough. The problems of pressure-sensitive hydraulic lifters become worse as they start to wear and lose their closely machined tolerances. Shovelhead engines suffer this problem much more than the evolution engines, since the hydraulic lifters of the shovels are not machined with the same close tolerances as those of the Evo lifters. Evolution-style lifters are available with a standard outside diameter of 842.5 thousandths of an inch. An oversized lifter is also available with an outside diameter of 847.5 thousandths, or 5 thousandths oversize on standard. Running tolerances for evolution motors between lifters and the lifter block vary between 8/10 thousandths and 2 thousandths of an inch. In contrast, shovelhead motors have running tolerances between lifters and the lifter block of between 1/1000th and 2 thousandths of an inch. One way we overcome the shock absorber effect is to replace the stock hydraulic lifters with GIMS solid lifters, which are available for all big twins, including evolution engines. This conversion will also reduce the overall weight in our valve train. GIMS also makes the Power Glide high-performance hydraulic lifter kits for high-performance evolution, shovelhead, and panhead engines. GIMS claim that their Power Glide kits will eliminate the shock absorber effect of stock hydraulic lifters and simulate the performance of solid lifters. They also have the added advantage of being able to compensate for up to 40 thousandths of cylinder expansion, thus maintaining a zero valve backlash clearance to the highest RPM a Harley engine can safely turn. Power Glide hydraulic lifters are what we use when we are hand matching hydraulic components to a running fit of 2/10,000ths of an inch. Another benefit of the Power Glide hydraulic lifters is that they will also perform in stock tappet blocks and do not require special tappet blocks until the lifts of our cam passes 550 thousandths. GIMS claim that their superior performance is due to a state-of-the-art tungsten disulfide coating, dicronite DL5, which greatly reduces the coefficient of friction on the lifter bearing surfaces. In addition, GIMS use exacting production tolerances and precise machining methods in their hydraulic lifter kits. If you have a 1984 or 1985 80-inch Evo, you will need to upgrade your hydraulic lifters, since the factory increased the size of the hydraulic pistons in their lifters by approximately 40 thousandths after 1985. For the complete teardown and assembly of Evolution and Shovelhead hydraulic lifters, please refer to your copies of the Shovelhead motor and Evolution motor video manuals. Solid lifters are constructed in one piece and do not have any hydraulic damping units. Therefore, they will not overpressurize or collapse intermittently with oil pressure variations due to temperature or RPM fluctuations. Aftermarket solid lifters are lighter and are also available in shorter lengths. Use of shorter lifters reduces the excessive angles created when we use extra-long push rods in maximum performance engines that have longer cylinders than stock engines. S&S provide a conversion kit for Evolution-style engines that allows us to convert existing hydraulic lifters to solid adjustable lifters by replacing the hydraulic piston with a solid plug. When we use solid lifters, we must allow a gap of 1.5 thousandths between the rocker arm and the valve stem. We refer to this gap as valve backlash clearance, and it is a very necessary feature, since the solid lifters have no hydraulic cushion that serves to preload the valve train. When we use solid push rods with solid lifters, each lifter must have an adjustment screw and lock nut that we can use to provide the necessary valve backlash clearance. In Evolution engines, the solid lifter adjustment screw must also have an oil hole through it to allow the lubricating oil to flow up through the push rod to the rocker arm. There are also some negative effects that result from the use of solid adjustable lifters. By raising the seat for our solid push rods higher, we start to dramatically increase the angles between lifter and push rod, forcing the push rod further out of alignment and causing the push rod to rub on the push rod tube. In addition, the stresses experienced by the push rods during operation are dramatically increased as the angles between lifters and push rods increase. We prefer to use adjustable push rods and non-adjustable solid lifters and keep the angles as close to stock values as possible. Solid lifters are also noisy and require constant checking and adjusting to ensure that correct valve backlash clearances are maintained at all times. We must also understand that not all cams are able to run both solid and hydraulic lifters. It is extremely important that we check with the cam's manufacturer to see what types of lifters their particular cam will accommodate. Push rods, which are called either solid or adjustable, are the means by which our camshaft is able to open and close the valves in our engine, giving us our valve timing. When we refer to a push rod as solid, we really mean that it is non-adjustable. All push rods are actually hollow, made from tubing to conserve weight and for greater strength. We prefer to use adjustable push rods with solid non-adjustable lifters in our engines. The benefit of using this combination is that we will not dramatically alter the angle of our push rods in relation to their lifters, thus preventing the push rods from rubbing on their covers. In stock Evolution engines, oil is pumped up through the center of non-adjustable hollow steel push rods and forced into the centers of their rocker arms. These rocker arms then direct the oil flow directly onto their respective valve springs. The ideal position for our push rods relative to their respective lifters would be 90 degrees. But unfortunately, this is not possible using a single camshaft. The stress on our push rods increases the further off-center they are. The worst stresses act on the front exhaust push rod on any big twin engine. These stresses are greatly increased when design modifications are introduced that increase valve lifts or spring pressures. As a general rule of thumb, we limit the use of adjustable aluminum push rods in Evolution engines to camshafts with valve lifts less than 550 thousandths of an inch. Cams that have valve lifts over 550 thousandths cause aluminum push rods to flex and fail under the extra valve spring pressures and stresses of this design. The combined effect of the aluminum push rods flexing and the hydraulic lifters pumping up and collapsing further disrupts our sensitive valve timing. When our valve lifts exceed 550 thousandths, we prefer to use adjustable chrome moly steel push rods. The chrome moly steel push rods are slightly heavier than aluminum push rods, but they are also much stronger, more rigid, and less likely to fail in high-performance engines. Before we install each push rod, we check it for straightness. Placing the push rod on a granite surface plate We use a flashlight to see if any light passes between the push rod and the surface plate. If we do see any light, the push rod is bent and should be replaced before installation. There are normally only two reasons why we find a bent push rod. It is either too weak to handle the valve spring pressure, or the valve springs have become coil bound. Most cam manufacturers will recommend the type of push rods they want used with their high lift cams and heavy valve spring pressures.